two terms you can't take anything out, but if you go for second term, so if you use second and third, you can take b outside. You can take b outside, okay? or or let me show both things, or you may get confused. See here, see, first two terms I cannot anything out, correct, right? But if you go for second one means BC and A bar B. So if you take these two terms, you can take B outside and you will get A bar C. A bar C plus B bar C bar. Correct, right? Instead of doing this, so check the first one and second one. First for F1 and F2. So in both the equations, A bar B and A bar B are common. Correct, right? So when we have A bar B common, if you keep those terms as it is, we can reduce the number of gates. We can reduce the number of gates. That's the reason what I am going to do with the F2 here is, instead of taking these two products, instead of taking B common, I will keep this A bar B bar as it is, and these two terms B bar C bar plus BC, what can I write? B bar C bar plus BC, what can I write? If you remember the Boolean algebra, you can write. What can I write with this? B bar C bar plus BC. Any idea what can I write that? Those two product B X nor C. B X nor C. So what is the full expression? What is the expression of that, Ankita? Expression of X nor when the inputs are A, B, and C. So what can we write that? We can write this is equal to, just that is equal to B bar plus C into B plus C bar. Is this correct, guys? Is this correct? B bar plus C, B plus C bar, and A bar B right as it is. A bar B right as it is. Hope you people are clear why I kept A bar B as it is. So if you take last two terms, you can take B out. So you are left out with A bar plus C. So why I retained as it means, so in the F1 function I have A bar B. So here also I have A bar B. Here also I have A bar B. If I retain this product as it is, I can reduce the number of gates. Means for F1 and F2, these two will be common. That's the reason I kept. So these two products I have, this is the expression is like a X or not gate. So I have written the expression like this: B bar plus C into B plus C bar. Similarly, check the F3. Check 3 F3. So here I can't take anything common. If you take AB plus BC bar, AB plus BC bar, you can take B outside. You can take B outside. This is equal to A bar, B bar, C, A bar, B bar, C, plus take B out, take B out. So A plus C bar, A plus C bar, A plus C bar. Any more simplification? Is it possible to do any more simplification of F1, F2, F3? No. So which gate they asked us to construct? They asked us to use which gate? NAND gate, correct, right? Now we need to construct the NAND gate circuit, which is going to give the three functions F1, F2, F3. So that is 2 input NAND gate, correct, right? So let us take F1. Let us take F1. Okay. So in the first term, I have B bar into C bar plus A. So first I am going to write this C bar A. I am going to write. So A C bar A C bar. Correct, right? This output I will get A plus C bar. In this I will get A plus C bar. So this into B bar. This into B bar. So take one more and get. So this is D bar. Okay. So this gives this entire thing. This output of this NAND gate gives the B bar into C bar plus A. So take one more NAND gate for A bar B. Take one more NAND gate for A bar B. So A bar B, then these two. So this term into this. So that is going to give the F1. That is going to give the F1. So this gives F1. This gives function F1. We are used uppercase. Let's use the uppercase one. So this gives F1. Similarly, we need to write F2. Similarly, we need to write F2. We are not going to take the separate. We are going to join for this one. So F2, what and all we require? F2 we require B bar plus C, B bar plus C and B plus C bar, B plus C bar. So take this B bar C and one more NAND gate for BC bar. B C bar. So to combine these two, one more NAND gate. One more NAND gate. Okay, this NAND gate gives this term. This NAND gate is going to give this term. So next we have A bar B. See, already we have a gate for to obtain the output A bar B. So that is from where? Here, A bar B. So combine these two. Combine these two. So this will give F2. This will give F2. Similarly, we need to write it for F3. Similarly, we need it to write for F3. Next, we have B bar C. See, A bar, B bar C. A bar, B bar C. So, do we have already to obtain B bar C? See, B bar C we have already, correct, right? So to get that as a B bar C, we need to use the inverter here. We need to use the inverter here because here B bar C after NANDing here, what will happen? It is like a BC. It is like a BC, correct, right? Again, I want to retain this as it is. So what I'm going to use here? So I'm taking one more connection from here for F3. Let me take from this. So here I'm going to use inverter. Inverter means that is your NOT gate to retain P bar C as it is. To retain P bar C as it is, because here we have used NAND gate, so it will be inverted, correct, right? I want to retain this B bar C as it is. That's the reason here I'm going to use the B bar C. B bar C. So now I got B bar C. So output of this will be get added with A bar. This will get added with A bar. So from this NAND gate, I will get A bar B bar C. A bar B bar C. Next check. Do you have for A plus C bar? Do you have gate for this A plus C bar? I think we have it. Check where A plus C bar do we have? Yes, we have in F1. We have in F1. See here, A plus C bar or C plus A bar. So where it is? Here it is. So I am going to take from here. Guys, while you people writing in the notebook, write it properly. Connection. So I'm going to obtain this, correct, right? A plus C bar I got from here. A plus C bar I got. Okay, this should get added with B. That should get added with B. So from this NAND gate, I got this term. From this NAND gate, I got A bar B bar C. Now add that with another NAND gate. Add that with another NAND gate. You will be getting F3. You will get F3. Is the circuit is correct? The circuit is correct. Is the circuit is correct? Check once. Is it correct? Okay, copy it. Copy it. Can you write down from the circuit what I have written, or you want textbook diagram? Can you copy from the circuit what I have written, or you want textbook diagram only? Can you copy from that? Okay. So that is also same. Only the thing is there. Just copy this second one. Copy the second one. So no need to write the with or gate. You will be confused. So take down only the second one. It is what I written, it is same like this only. The way of representation is different. That's it. They have maintained level by level. Neatly they have written. Once you copy, drop the message in the chat box. Finished? Guys, finished? Write fast. How long you want to copy this? Any doubts in these two problems? See, they will give the min-term or function. So you need to plot the k-map. So after plotting the k-map, just write with the expression. So if they ask you to construct NOR gate, then we are going to write the SOP, correct, right? Sorry, POS. If you write the expression in the POS form, it will be very difficult for simplification. So instead of writing F, so I'm speaking of the first problem. So instead of writing F, write F inverse. So F inverse means you will be grouping for 0 only, but you will be writing the expression in terms of SOP. Then minimize it, then write the F. So how to write? So wherever inverse is there, write as it is. Wherever A is there, make it as A bar. Wherever A bar is there, make it as A. Wherever A is there, make it as A bar. Wherever dot is there, make it as a plus. Wherever plus is there, make it as a dot. Suppose if they ask you to write the SOP form and NAND gate, directly you can write F instead of writing F dash, because directly we can simplify it. Okay, simplify, then rig up the circuit by using the given gate. Any doubts in these two problems? Next we have gate delay and timing diagram. Gate delay and timing diagram. So what is this gate delay and timing diagram? So we have logic circuit. So we are able to change only the inputs, correct, right? So whenever we are going to change the input to a logic gate, the output will be changed immediately, or will it take some amount of time to change? Now you have a logic circuit. You are going to change the input. Correct, right? When you change the input, the output will be changed instantaneously, or will it take some amount of time to change? Guys, I want you people to answer from this. As soon as you change the input, will it take some amount of time, or will it change instantaneously? Chandrakant saying takes some time. Lavanya changing instantaneously. Akshata sometime. Sometime there will be a delay. Yes, Lavanya, it won't change instantaneously. But for us, it will look like it is changing instantaneously or immediately. But inside the gate, it will take some amount of time. It is some amount of time is, it is in the sense of nanoseconds. So that nanosecond is nothing to us, correct, right? That's the reason we may feel it's instantaneous. Actually, when we are speaking practically, actually as soon as you change the input, the output won't change instantaneously or immediately. It will take some amount of time. Why it is? So there will be a transistor or other switching element within the gate. There will be a transistor or some other switching element within the gate, so it takes some finite amount of time to react for the change of the input. Sometimes initially it will be in the zero state. Okay, when you have zero input, the output will be something. So when you change the input from 0 to 1, so there will be a transistor or switch inside the gate, so that takes amount of time to switch from 0 to 1 itself. It will take amount of time to switch within the gate to a 0 to 1. So that causes the change of the gate output delay. So when it is going to take the some amount of time to switch from 0 to 1, at the output side also there will be a delay with respect to the input change. Means there will be amount of time taken by the output gate to give the out changes. See, you can look at the diagram here. So here you can look at the diagram. Here I have the NOT gate. Here I have the NOT gate. X represents the input, X bar represents the output of the NOT gate. Correct, right? So here initially the value of the X is 0. The value of the X is 0. At this time, at this particular time, the value of X is changed from 0 to 1. I think you can observe here. So till this time, the value of X is 0. At this particular time, the value of X is changed from 0 to 1. So when the value of X is input, the output of the NOT gate will be high, means it will be 1. See, in this particular time the value of X is changed from 0 to 1. So after the value of X changed from 0 to 1, the output will be reverse of that, correct, right? But here the value of X is changed from 0 to 1. See, after this amount of time. After this amount of time means at this particular time. At this particular time, the output of the NOT gate is changed from 1 to 0. So this difference is represented by the epsilon 1. So epsilon 1 represents the amount of time taken to change the output. Okay, epsilon 1 represents the output delay. So this we can tell it as a change in the output delay, change in the output delay time. Similarly here also you can see, so at this particular time the input value of x is changing from 1 to 0. It's 1 to 0. See, after this amount of time the output is changing from 0 to 1, 0 to 1. See, you can observe here. So here I have two output delay, one is epsilon 1 and epsilon 2. Are they same? Are they same? Are they same? They are not same, correct, right? So what we can say here is propagation delay. This we will say it as a propagation delay. Propagation delay for 0 to 1. Propagation delay for 0 to 1 output change may differ than the delay for 1 to 0 to change. Means when it is changed from 0 to 1, what is the propagation delay you have, that may change to the propagation delay from 1 to 0. It is not necessary that the epsilon 1 and epsilon 2 both should be 0. It can be changed or they may be differ. So this propagation delay of the integrated circuit may be short. May be short means it will be in terms of nanoseconds. These things will be in terms of nanoseconds. So in many cases we are going to neglect it. In many cases we are going to neglect it. Yes, are you clear? What is the delay? Are you clear with this? What is propagation delay? Propagation delay means as soon as you change the input of the logic circuit or IC, the output change won't change immediately or instantaneously. After the propagation delay, after some amount of time, the output will be changed. Next, we'll move to the timing diagram. What do you mean by timing diagram? So next we have timing diagram. What is this timing diagram? So however, the input will be changes in the gating logic gates that will be represented in the timing diagram. That's it. So in this particular example or in this particular example, I have two gates. I have two gates, gate 1 and gate 2. Gate 1 is the AND gate, gate 2 is NOR gate. AND gate and NOR gate. So what are the inputs for AND gate? A and B. For NOR gate, G1 and C. G2 is the output of the entire circuit. Correct, right? So initially, see here. So in the circuit given below, each gate has a propagation delay 20 nanoseconds. So this is the timing diagram. Timing diagram for this logic circuit. So each gate has a 20 nanoseconds of the propagation delay. Each gate has the 20 nanoseconds of the propagation delay. B and C inputs are held constant with the values B equal to 1, C equal to 0. So the value of B equal to 1, the value of C equal to 0. Only here I am going to change the value of A. There are three inputs A, B, C. B is kept constant 1, C is kept constant as a 0, just I am going to change the value of a here. Okay, so see here, when the input a is changed from 0 to 1, see initially the value of a equal to 0. Initially the value of a equal to 0. It is going to change from 0 to 1. The value of a is going to change from 0 to 1 at 40 seconds. At 40 seconds, we'll see till 40 seconds what will be the output. Okay, so what is a value initially when time equal to 0? A is 0, so b equal to 1. When one of the input is 0, AND gate output will be 0. So G1 is 0. See, first 20 nanoseconds, G1 is 0. So G1 is 0, C is 0. Even G2 will be 0 because both the inputs are 0, the output will be, so sorry, this is not OR gate, this is not NOR gate. So both the inputs are 0 means OR gate output will be 0, but here we have NOR gate, so inverse of 0 is it's 1, so the output of G2 will be high. Output of G2 will be high for first 20 nanoseconds. But what time it is going to change? It is going to change at 40. So remaining 20 nanoseconds, the things will be as it is. See, next 20 nanoseconds, the waves will be same as previous 20 nanoseconds. Are you clear till here? Guys, are you clear with this? First 40 nanoseconds. Okay, so when there is a 40 nanoseconds, when time comes to 40 nanoseconds, the input value of a, it is going to change from 0 to 1. It is going to change from 0 to 1. See, at 40 nanoseconds, the a is going to change from 0 to 1. Hope you can see it is going to change from 0 to 1. So now it is changed to 1. Now it is changed to 1. So when A equal to 1, B equal to 1, G1 should be 1. Correct, right? That G1 will be changed from 0 to 1 at what time? Immediately 40 nanoseconds, or it will take some delay to change it? 40 it is changed. Correct, right? So at 40 nanoseconds itself, G1 will be changed, or it is going to take some amount of time to change. It will take some amount of time, right? So how many times we taken here? What's the delay amount we are taken? 20 nanoseconds. So 40 plus 20, 60 nanoseconds. So at 60 nanosecond, the output of the G1 will be changed. See, output of G1 will be changed at after delay. See, 40 at 40 nanoseconds, A changed from 0 to 1. But immediately G1 is not going to change. G1 will be changed after 20 nanoseconds because this 20 nanoseconds is your propagation delay. Now G1 is changed from 0 to 1. G1 is changed from 0 to 1. Now G1 is 1. G1 is 1. So this is 0. This is 0. Correct, right? 0 and 1, the OR gate will be 1, but NOR gate will be 0. At 60 G1 will be changed. So when G1 is changed, G2 also should change. What time G2 will change? After adding the propagation delay. So after 20 nanoseconds, after this propagation delay, the G2 is going to change from 0 to, sorry, 1 to 0. It will change from 1 to 0. See, 80 nanosecond. After 20 nanoseconds of propagation delay, it will change from 0 to, sorry, 1 to 0. Now we'll check again. So at 100 nanosecond, again A is going to change from high to low. 1 to 0. But immediately at 100, it's not going to change. After 20 nanoseconds, G1 will change from 1 to 1 to 0. Even after G1 is changed, G2 will not change immediately. G2 is going to change after 20 nanoseconds or after 20 propagation delay. After 20 nanoseconds, it is going to change from low to high. Low to high. This is the way how we are going to write the timing diagram. Guys, are you clear? Are you clear with this? Because we have next problem I have. I will give for you people to solve it. If you are not clear, please now itself ask. Is just keep it in the mind. As soon as you change the input value to the circuit, immediately the output won't change. So whatever the amount of delay they have specified, after that delay, it is going to change its input. Sorry, its output. That's it. It's clear, right? Okay. I have one more example. Let me show that also. With delay I have. See here. See, in this example, I don't have any other gates apart from AND gate. I have only one AND gate. So that AND gate, in that AND gate, I have one extra element called delay element. So in this diagram, I have a circuit with added delay element. So this part, I am speaking of this part. See, I have only one AND gate. Only one gate in the circuit. So this circuit is added with one added delay. One added delay. So that for added delay, X is the input, Y is the output. So this is the timing diagram for this. So here the delay is specified as a 1 microsecond. So in the previous graph, that is 20 nanoseconds. So if they ask the question to plot the timing diagram, they only will give the delay. Okay, in this diagram, in this timing diagram, the propagation delay is 1 microsecond. Okay, let's speak of this. See, so this is the added delay element to the AND gate. So look at this. Look at this. I have X, I have Y, I have Z. X is the input. One input to AND gate. One input to added delay element. Y is the output of the added delay element. Then Z is the output of the AND gate. So in the X, so at X, I have two pulses. I have two pulses. So for the input X consisting of two pulses. So first pulse with 2 microseconds and the second pulse with 3 microseconds. First pulse with 2 nanoseconds and second pulse with 3 nanoseconds. So the delay element is going to have output Y. Correct, right? See here, first 1 microsecond, the value of first 1 microsecond, the value of X is 0. The value of X is 0. Correct, right? So when you give 0 to the delay element, it will give 0 only. It will give 0 only. At time 1, at time 1, the value of X is changed from 0 to 1. The value of X changed from 0 to 1. So here we have an added delay. So the output Y won't change immediately. The added delay output Y is not going to change immediately. So this output of the added delay is same as your input X, but it is delayed by 1 microsecond, which means that Y changes to 1 y change to a 1 value after rising edge of the x pulse. See, so this is rising edge of the pulse x. After rising edge of the pulse x, after 1 microsecond, the value of x is changing. See, x and between x and y, I don't have any gates. Just I have an added delay. The output of the y is same as x only, but because of added delay, after this rising edge of x, after the 1 microsecond of this, the y is going to change the value here also. After changing this, see, rising edge, so this is the falling edge. After the falling edge, after 1 nanosecond of the falling edge, it is going to change. Can you make a note of x and y? Both are same, pulses are same. Just after 1 nanoseconds of the rising edge and falling edge of x, the output of the y is changing. Are you observing? See, both x as well as y are same. Okay, only the difference here is I have an added delay here. Because of this delay, the y is going to change after 1 nanoseconds of rising edge and falling edge. That's it. Yes, everyone slept or few are awakened. That is the function of added delay. Now we'll see what happens to the AND gate. So exists the input for both AND gate as well as the output added element. So that output y is the same as x, but after 1 nanoseconds is going to change the pulses at the rising edge as well as the falling edge. What is the how this AND gate will be work? When both the inputs are high, z will be high, otherwise it is low. Okay, check here x and y. So initially x and y are 0, so the AND gate is 0. Next 1 microsecond, this is 1, this is 0, so it is 0. Correct, right? Next here, so x is 1, x is 1, y is 1. See, previously x is 1, now y is 1. Both the inputs are 1. Both the inputs are 1 means the output of the AND gate should be 1. Both the inputs are 1 means output of the AND gate should be 1. See, can you make a difference here? Small difference. I'm writing. What is that small difference? What I marked here? What is this small difference? What is that small difference? So that is delay. That is nothing but delay. See, at time 1, at 2 microsecond, the y is changed from 0 to 1. So now both the inputs are 1, the AND gate should be changed to 1. But what will happen here? See, there is a small amount of delay here. So the z is not going to change immediately from 0 to 1. It is taking some amount of time after y has changed from 0 to 1. After this amount of delay, the change is z is changed from 0 to 1. Okay, it is changed from 0 to 1. Now it's in 1. Now till 3 it's 1. We'll see at time 3 what happens. So in the time 3, at time 3, x will become 0. X will become 0. What about y? It's 1. When it is 0 1, z should become 0, correct, right? When it is 0 1, z should become 0. So exactly at 3, x will become 0, correct, right? When it is 0, of course the output of the z should go to 0, but exactly at 3 it's not going because of delay. So this is delay, this is delay. So after this amount of delay, z will change from 1 to 0, z will change from 1 to 0. So that is the first 2 microseconds of the x pulse. We'll see what will happen in the next 3 microseconds of the second pulse of x. See, at 6 microsecond, at 6 microsecond, the the x will change from 0 to 1. It will change from 0 to 1. When it is changed from 0 to 1, immediately y is not going to change. Immediately y is not going to change. It will be retained as it is. It will be retained as it for the 1 microsecond. After the 1 microsecond, the y is going to change. After 1 microseconds of the falling edge, sorry, here it's rising edge. After 1 microsecond of the rising edge, x will be changed its state from 0 to 1. Again at time 9, again at time 9, the x is changed from high to low, high to low. After 1 nanosecond, after 1 nanoseconds of the falling edge, the xy will change the state from high to low. It will change from high to low. Now we'll see the z value. We'll see the z value. So here it is 0, here it is, sorry, here it is 1, here it is 0. So it is 0 only. This time means at time 7, at time 7, y is changed from low to high. Y is changed from low to high. Means in this duration both are high. In this duration 7 to 8 both are high, because at 7 it's changed to 1, correct, right? When the both the inputs are high, I should get z as a high, but immediately at 7 it's not going to change. Immediately at 7 it's not going to change. It's taking amount of propagation delay, or it is going to take some finite amount of time to change its state from low to high. It's going to change from low to high. Again, check the next slot. So this is high, this is high, so this will be high, it will be continuous. Check at 9, time 9. Check at the time 9. Again at time 9 microsecond, the x is going to change its state from high to low. It's going to change from high to low. So what is the value of x at 9? It is 0. Here it is 1. When it is 0 1, the output I should get it as a 0. But exactly at 9, the z is not going to change. After some finite amount of time, or propagation delay, after the propagation delay, the z is going to change its state from high to low, high to low. So this is how the propagation delay works with the your logic circuits. Guys, are you clear? Any doubts in the propagation delay and timing diagram? Any doubts in the timing diagram? Which webinar, Aditya? We didn't get any message. Aditya, which webinar? WhatsApp. One second, I'll check. I'm checking. Hey, is it for everyone? Everyone are going to attend. Guys, reply fast. Guys, that webinar is not for everyone, only for few. Those who are registered, you can attend the webinar, but be careful. From NSS coordinator, we are going to get the attendance. Okay, we are not going to wind up the class. Those who are registered, you can attend, but from the NSS coordinator, we will be getting the student list, those who attend. Okay, let me continue. Guys, any doubts in the timing diagram and the delay? Now I'll give the problem, you have to solve it. Copy this. Copy this and solve. Complete the timing diagram for the given circuit. Assume that both the gates have propagation delay of 5 nanoseconds. So for the AND gate and for the OR gate, I have 5 nanoseconds. Okay. X, Y, X, W, X, Y. W, X, Y are the inputs. V is the output of the AND gate. Z is the output of the OR gate. So find out V and Z. Find out V and Z. So if you are clear with that, you can solve this. Solve it fast. Let me see who will give the answer first. If it is wrong also no problem. Send the answer. Someone asking module 3 notes. Yeah, we will send. Wait, just now we started with module 3, right? Notes are here and there. We need to club and send. We will send. Guys, can you solve it? Or you want me to solve? Please reply for anything at least. If you are not replying, what should I understand? Oh, ma'am, you said okay, okay, guys. Two problems are there. One I will solve, but second one you people should try. Okay. So I have W. W and X are the input for the AND gate. Correct, right? First, let me complete V. First, let me complete V. So this year V starts. Okay. So initially W equal to 0, X equal to 1. Initially W equal to 0, X equal to 1. So because of the AND gate, V will be 0. V will be 0. Next, after 5 nanoseconds, next to start, W is 0, X is 1. W is 0, X is 1. Still, it is 0 only. Still, it is 0 only. Okay. Now you see, so at time 10 nanoseconds, W is changed from 0 to 1. At time 10, W is changed from 0 to 1. Correct, right? Now the W is 1, X is 1. When the both the inputs are 1, the output will be 1. But at 10 only, V is not going to change. See, at 10, input is changed. See, X is same, only W is changed. Once immediately W changes, the output is not going to change immediately. It is going to remain as it is for the next amount of delay. After the 5 nanoseconds of delay, we will change from 0 to 1. Next 5 nanoseconds, it will be changed to high. Now you check again, it is 1 1, it is 1. So at time 20, at time 20, W also changed, X also changed. So it is changed to 0 0. Both are changed to 0. At 20 itself, V is not going to change. For next delay, the V will be remained as the previous state. After this amount of delay, V is going to change from high to low. V is going to change from high to low. Are you clear with V? Are you clear with the output V, or are you clear with the output of the AND gate? Any doubts in the V? Any doubts? No. Okay. Karthik, repeat once again. Where you were listening? See, I'm going to derive for V. I'm going to write the waveform for the V currently. Okay. So what is the V? V is the output of the AND gate. What are the two inputs of the AND gate? W and X. W and X. See, first at 0, the value of W is 0. The value of X is 1. Correct, right? If either of one input is 0, AND gate will be 0. Correct, right? V will be 0. V will be 0. Again at time 5. Again at time 5, W is retained 0. Even X is retained as 1. Again, the output of V will be 0 itself. Correct, right? But at time 10, W is changed to 1. At time 10, W is changed to 1. X value is also 1. When both the inputs are 1, the output of the AND gate should be 1, but the V is not going to change immediately at 10 because of delay. So what is the amount of delay here? Amount of delay here is 5 nanoseconds. 10 plus 5, 15 nanoseconds. So at 15 it will be changed from 0 to 1. At 15 it will be changed to 0 to 1. 0 to 1. Now, okay, 110. Now you see, again at 20. Again at 20, W is changed from 1 to 0. Even X is changed from 1 to 0. Correct, right? Immediately at 20, the V is not going to change. At 20, V is not going to change. It will add plus 5 nanoseconds. So means this 5 nanoseconds, the output will be same as previous state. What is the previous state? Previous state is high. So the next 5 nanoseconds, it will be same as previous nanoseconds. At 25, it is going to change it from high to low, because here both are 0, so the output will be changed to 0. Karthik, are you clear now? Karthik, okay. Now we need to check Z. We need to check Z. So to write the timing diagram for the output Z, I need to concentrate on V as well as Y. V and Y. Both V and Y. So check V and Y. So both are 0. Both are 0 means Z will be 0. Z will be 0. Next nanoseconds also both are 0. So this is 0. Next also it is 0. It is 0. At time 15. At time 15, we change from 0 to 1. At time 15, we change from 0 to 1. Now it is 1 0. Now it is 1 0. But at 15 itself, Z is not going to change. It is taking 5 nanoseconds of delay. Then it is going to change at 20. At 20, it is going to change from 0 to 1. Okay. Now, what happened at 20? At 20, so this is also 1, this is also 1, this is 1. Again, what happened here? See here. So Y is 1, Y is 1. Y is 1, Y is 1 here. At 25, at 25, this is changed. V is changed. V is changed from 0 to 1. 1 0 is nothing but still it's 1 only. Still output is 1 only. So it will be retained. Output will be 1. But at 30 you see, at 30 you see, V is 0, sorry, Y is 0, Y is 0. Correct, right? So this is 0. V is 0. Even Y is changed from 1 to 0. So now both are 0 means the output should be 0. So the output change won't immediately at 30. Instead of it takes 5 nanoseconds, it will be changed at 35. It will be changed at 35. So this is the answer for this. Guys, are you clear with this? Are you clear with this? So once it will change the state, once if the input changes its state, at exact time it's not going to change the output value. After that amount of delay, it is going to change. Okay, no doubts, right? Then I will give the problem now. You have to complete it. Will you complete? Will you solve? Okay, fine. Oh, I have only one. I don't have another one to solve. Let me see, is there any questions? No, in assignment also same question is there. It's okay. Uh, it's clear, right? Otherwise, you have any doubt, you ask here only. I will explain. In assignment also same question. You have any doubts? So when I start hazards, there it will come. Next we have hazards. Okay. In the hazards also, writing the timing diagram will come. There I will give you people to write. Otherwise, if you want to write, take this. Take this circuit and write. Otherwise, now you leave. When I come to the other topic, I will give the same circuit to write. Okay, okay. But you don't have any doubts, right? Do you have any doubts in that? Timing diagram, any doubts? In the assignment also same question is there. Leave. When I will come to the hazard, I will give the circuit to write. Now give me the attendance. 1 to 5. Give me the attendance 1 to 5. One is absent, 3 is absent. Okay, next. 6 to 10. 6 to 10. 11 to 15. 16. 16 to 20. 18. 25. 26 to 30. 30. 31 to 35. 36 to 40. 39. 40. 41 to 45. 50. 51 to 55. 56 to 60. 61 to 65.
Ma'am, 61 present.
Uh, 66 to 70. 69 is not there. 69. 71 to 75. 76 to 80. 81 to 85. 88, 89, 90. Okay, guys, we'll meet it in the next class.
18 present, ma'am.
18, 1, 8.
Yes, ma'am.
Where were you when I called your number? Hmm?
Network problem, ma'am.
Oh, should I believe this? Only when I take the attendings, you will be having network issues. Otherwise, no issues.
I always have issue, ma'am.
Oh, let me see how many days you will be having. Okay, guys, we'll meet it in the next class. Two given, one given.
Ma'am, idea connection is very bad.
We'll give complaint to VI. Okay. Happy Dasara to all. Guys, given attendance 1980. Everyone I have given. Okay. Bye.